Welcome back to another lesson in Math 8. This is Unit 5, Lesson 11, Filling Containers, where we start looking into the volume of some figures. In previous grades, you would have been talked about the volume of a rectangular prism. In 8th grade, we talked about the volume of a cone, a sphere, and a cylinder. In this case, one of these, when we talk about these values right here, we need to figure out what is it about these 4 different shapes that's different. So we say what doesn't belong. And we can talk about just a couple pieces with it, such as the cone. We'll start with that one, part A. Why doesn't it belong? Well, in this case, this is the only one that has exactly 2 surfaces. When we talk about a surface, we're talking about a plane that can be laid out completely flat and be all intact in one object. And you might be saying, well, B has 2 different planes, the top and the bottom. Let me build on that just a little bit. I'll talk about this one right here. Well, I'll talk about it now. This is not called a planar face. This is just going to be a cylindrical, or excuse me, a spherical face because of the way that it's shaped. A planar face has to be a flat face with actually with an actual edge. I'm sorry. That edge would come up if I were to cut this along some kind of a line all the way around. That edge would happen. In this case, that same fact doesn't happen with the plane on a sphere. But the other piece with this is the one of those 2 surfaces is its base, and it's the only one of the figures right here that has just one single base. By a base, we're talking about it has to be a side of a figure that's flat and can sit on a flat plane without going anywhere. B can't do that because that's a ball. It's ultimately what it is, and it would roll around. This figure also has no edges, no planar faces, such as all these other ones. Planar faces meaning a flat face. It's also one that's not stable. If you set it down, it's, like I said, it rolls around. Letter C is the only object that has the side is an actual rectangle in 2 dimensions. So if you were to cut this one along the side and roll it all out, it would be a big rectangle, but it's 2-dimensional, and it has a 2-dimensional length and width. But when it's wrapped around the bases, it becomes a 3-dimensional figure. Kind of cool, from 2-dimensional to 3-dimensional. It's also the only one that has exactly 2 bases, with the top and the bottom being those bases. Letter D it's the only one with all of the faces being flat, which means every one of these 6 faces could be a base, depending on how this rectangular prism is laying. It's also the only object with rectangular faces. So, kind of interesting facts with all of those pieces. I'd be interested to see what kind of differences you said, why they don't fit. Maybe that's the only one that has a pointy top. Yeah, absolutely. Okay. When we move on with this, we talk about 11.2 is the height and volume. There's an interactive set for this that I would encourage you to open up and play with. I'm going to do that here in a second because I would love to give you graduated cylinders and water to actually play with and do this in real life. That'd be a lot of fun. But given our circumstances, we need to do this a little differently. We're going to use this little applet right here. If you punch in that link that was given there, we're going to actually fill this cylinder up. And then on our next page, right here, we have a data table that we're going to fill out. And in that data table, we'll collect the data, and then we're supposed to graph it. The cool thing about this little applet is once I have that data, I can go down just a little bit further from this other one where that link takes me, and I can add in my data points, and it will graph it for me. So, whoops. Here we go. Now that I just messed up my plane. Oh, there we go. Okay, that's where I wanted it. All right. So what we're going to do is we notice that right now this is a 10 milliliter graduated cylinder. It has a diameter of 5 centimeters, so halfway across has 2.5 centimeters for the radius. We are going to be measuring the volume and the height. And I don't know why that just moved, but here we go. Click on fill and pause, and I'm just going to stop at random times. 10 milliliters, 10 and 1/10. I'm recording this on my table. You can go ahead and do it too. Has a height of 5/10 centimeters, so it's going to look like this. The next one, fill it up some more. I'm just going to try and get close to an average of 10 milliliters and then see what happens. That one. A little bit far. So we've got 32 and 8/10 and 1 and 7/10. I'm doing pretty terrible at this. 46 and 6/10, 2 and 4/10. So I'm going to be done trying to get a constant rate. But the cool thing about this is no matter what I do, I'm going to get a constant rate because this is a proportional function. Proportional because of we start out with nothing. And so it starts out with 0, 0 for the y-intercept. And we see it growing. We'll see that it grows at a proportional value. So here we go. Here are our data right here. And I'm going to take these same data right here, and I'm going to put them into this little table right here. So we had 10 and 10. Feel free to pause the video and go ahead and update all of your stuff. Keep watching, whatever it may be. Now, I've kind of done this on purpose where you can't see all of the data, but think about it right now. Looking at these data, we see just a couple of the points right here, a couple of the 6 pieces of data that we collected. But as we zoom out and we start to see more, we notice that these points are actually linear. And that's a pretty cool thing, which means that what we have right here is a linear function. It tells us that the height of the cylinder is a function of its volume. And that what it means is that it's filling at a constant rate, yes, but what we know about this is that the height is a function of the volume because at any point, the input of the volume, there is exactly one volume that would happen at a time, and that output of the height can have exactly one input that goes with it. So there's never a spot where we would actually have on our input, there's never a spot that we can actually repeat that input because there's exactly one volume, or excuse me, exactly one height for each volume. And those volumes, it's perpetually changing. As you add a little more, the volume automatically changes. There's nothing else that can be done about that. And so as a function here, it's really important that we recognize that that these values inside here are going to be, or that volume is actually a functional situation. And so what we notice about these shapes in our graph is that we see straight lines. We notice that the independent variable is the volume, and then the dependent variable is the height. So the height really depends on how much water we put into it. It doesn't differ much from what I thought it would look like. I thought it would be a straight line. And for that last question, what point did you choose? Let's talk about that. I haven't talked about that yet, but let's look on here. We're supposed to choose a point, number 5 or number 4 that's down here down at the bottom there of our paper. I'm supposed to choose any point. If I chose this point right here, 54 and 3/10, and then 2 and 8/10, and I go back and I look here at my table, what does it actually mean? Well, that ordered pair of 54 and 3/10 and then 2 and 8/10 means that at a volume of 54 and 3/10 milliliters, the height in my cylinder is 2 and 8/10 centimeters. Now, what you can do with this is you can actually go back and you can play with it. You can reset this value, and then you can change the height of the figure, and look what happens. You can change the radius of that figure, and we get something that's much, much bigger. And then we start filling it up, and we notice that this height of 1 and 4/10 centimeters, that's not too far off from our third point. I'm going to go ahead and mark this on here. We've changed just a couple of factors with this. A height of 1 and 4/10 centimeters gave us 109 and 6/10 milliliters. And when we compare that to what we had before, just by changing the height of the figure and the diameter of the figure, for relatively the same height of water, I get way more water. So what we can see with this is that that function is actually even bigger than what we noticed before when we looked at that point. And we talk about the context of this point right here. If I were to continue going with that, let's see how close I can get to 2 and 8/10 of a height. 2 centimeters. This is now the exact same thing, but my volume now is, I'm going to go ahead and write it on here so we can compare it. My volume now is so much greater. What this all tells us when we talk about those pieces is that if I change the size of my cylinder, I am also changing the height of the water and how fast the water goes in. But if I change those pieces, it's a much bigger difference in the volume, or excuse me, much bigger difference in the slopes that were occurring here. My slope became much, much, much slower in this container, in this first part. So it'd be kind of looking like this. My data would kind of go like this, pretty steep. And then if I were to look at this in ones, it'd be pretty steep like this if I were talking about a much smaller container. And then the larger container would taper off to a much more gradual slope. And so what we can see is we can actually see that here in our next segment. It says, what is the shape? If we have a graph that's showing height and volume, and the function of an unknown container, it says, what shape could this container be? So explain how you know and draw a possible container. And this is just an example of what I was talking about. If that volume is filling up, or if the height is filling up quite rapidly compared to the volume in milliliters, when we look at this, this is if these little ticks were by 1, if my intervals are all by 1, this ordered pair would be 9, 4, and I would see a slope of this section is 9 and 4. The next one would be at 1310, and excuse me, I'll get it wrong, 1310, and my slope would be much more gradual slope. It would be a slope of 6 over, let's see, 10 was that, 13, 6/4 or 3/2. Oops, sorry, I wrote that wrong. That one rises at a rate of 1, 2, 3, 4 over 6. Okay, I'm sorry about that. I messed it up. So, but we see that that's a much different slope right here. This one is greater than 1. This one's less than 1. And so what we see is we see on this one a tall cylinder, kind of tall and narrow. And this one we see as shorter and wider. The reason for that is because the volume is increasing at a much slower rate and the height is also increasing at a much slower rate. So we have to think about it as something like, maybe take like just a small cup that you're using for a kitchen glass, and you're filling that little cup of water for a drink. Now imagine changing over and grabbing a pitcher and filling that pitcher up to serve a whole bunch of cups of water. The difference would mean that this small one is going to fill up very rapidly. It's smaller and it's narrower. And this one would actually probably be a little bit taller than that. This other one, which should be shorter and wider, or maybe it's just something that's just being compared, but you get the idea that the size of the figure dictates how quickly it's going to fill up. You could even go to the extreme side and say fill up a 5-gallon bucket from your sink faucet. It's going to take a long time, right? This one is the idea is that these two segments are going to, or these two pieces of this function are going to represent 2 different pictures. So let's look at one more picture that actually has 3 segments, and you guessed it, that will actually be 3 different figures or 3 different pieces. This first order pair is 40 milliliters, is 9 centimeters tall. 50 milliliters is 11 centimeters tall. And then the last one, 80 liters or 80 milliliters is 13 centimeters tall. And we see that those rates are all filling at 3 different rates. So we would have to say there's 3 different containers. And what those 3 different containers would have to look like is you'd have to have a really tall, skinny one for the bottom, for this one right here. The next one would have to be much shorter because the volume filled up a lot more. It's only a 10 milliliter volume, but it also filled up really quickly. So it'd have to be something like that. And then the last one is going to have to be the shortest one of all. It's going to be really broad or really wide, but it's going to be something like that on top because it fills up very slowly, but it's also very short, so we know it fills up very quickly. So just some kind of ideas for how they are. What do we think when we're talking about the two containers? How are they similar? How are they different? What we're talking about is the container that represented this situation compared to the container that represented this situation is that container 1 has 2 parts. And container 2 has 3 parts. And we can use that whole piecewise function to be able to look at the two of them and figure out those different pieces that we're filling up at different rates. We can also recognize, I forgot to talk about their similarities, I can make them all from stacking up cylinders. And we can look at those pieces to recognize different cylinders because we use them all the time in our life and we fill them up all the time. And it's something that's kind of realistic. So what we have to realize with all of this is that filling up cylinders with water is actually a function of life. And we talk about filling up the water. We know that filling up those cylinders, when we change the height, or when we change the height of the cylinder and the width of the cylinder, it creates different rates of filling it up. So if we pour water into both of these two cylinders, the result is this. Letter D, this cylinder is going to fill up much, much faster because obviously it's a smaller container. And what makes it smaller is that radius. Even though the height is taller, it's a smaller radius. So the volume is going to increase much more rapidly than this one right here when we're talking about a given flow rate. If we pour them in at the exact same rate, what we're going to see is this one's going to increase very rapidly while the other one will increase very slowly. So we're going to say this one has a steep slope and this one has a mild slope. So it's going to be not really steep, but it's just going to continue up. If we made a graph that represents the height of the water as a function of the volume, we would see that the two lines of these slopes in this cylinder would be, D would be much greater, like this, and then E would be something like this. That's the gist of today's lesson. We're going to get a lot more into the volume of things, but right now we're just trying to tie volume into a function and recognizing that this. If we flipped all this around and we talked about it, we saw that height is a function of volume. Okay, the water height, I should put that. Water height is a function of volume. What we're going to find out if we flip this around and we say that volume is dependent, volume is a function of two things. This is your little preview of height and diameter of a cylinder. So meaning that the volume is also going to change, but it's based on two factors. So there's your little preview. Thanks for checking in. Let me know what I can do for you and helping you out in this next task.